Okay, let's see if we can record another podcast without the noise. Still waiting for the new laptop. So here is the data from Woods Hole ship Nor, which went out there in Labrador Sea in fall and the winter months of 96 into 97. These are showing the stratification as d sigma dz with sigma contours on top, and in the fall months you are just coming out of the summer surface heating and stratification, so you can see strong stratification near the surface, and various processes create this mid-level collapse of stratification from about 1 kilometer to 2.5 to 3 kilometers, and the stratification increases again at the bottom from the previous winter or from the non-local flows of deeper waters, right? By March 97, the winter is beginning to end, and you can see that the surface buoyancy loss has created the collapse of the stratification down to 3.5 kilometers or so. And you can see that the entire surface water doesn't collapse. There are plumes, as we will see in the next figure. And you see these high stratification water masses still stuck there, but in general, the heavy water from the surface has cut through the stratification and created this fairly uniform vertical homogenization of density, which can be seen here as mixed layer depths. You have stratified waters off the shelf of Greenland and shelf of Canada, whereas you have in the middle of the Labrador Sea deepening of the mixed layers compatible with this vertical homogenization with mixed layer depths of down to 1400 meters. Mixed layer depth is not exactly well defined in these cases, but we will just stick to the vertical density gradient being very small. So the preconditioning of October 96 would be something like this, with high stratification near the surface, mid-depth weak stratification, and strong stratification at depth. And the convection and mixing happens because of these squiggly lines, which are huge buoyancy losses because of the very dry, cold continental air from the Arctic blasting onto the Labrador Sea and picking massive amounts of latent heat loss because the ocean is still fairly warm compared to the atmosphere and the continental air. So you can see these circles, which are the local plumes that sink, and for each parcel of water that comes down has to be replaced by another parcel for mass continuity reasons, of course. You cannot create a hole in the ocean. So you can see those plumes being shown. And once the convection phase is over and the mixing has happened, sinking and spreading happens. So as spring proceeds into summer months, the re-stratification at the surface begins to take place, and the water that has sunk in the winter months finds its neutral buoyancy place and then spreads out in the horizontal, of course heading to the west coast and down to the south. And the deeper western boundary currents were first predicted by Henry Melson Stommel. The guy did amazing science, really a giant in the field of oceanography. Started as a young person in Woods Hole, went to Harvard and MIT, never got a PhD, by the way, but his work is so amazing that it's worth 100 PhDs. Okay, so we have been saying how slowly the deep ocean moves and currents cannot be measured directly at all. Henry Stommel, on the other hand, said, but there should be measurable currents on the western boundary, even in the deep ocean. And surely enough, the western boundary currents were measured off of Woods Hole at some point based on his predictions. Okay, but so before any data was available, he was able to go by physics and say there should be a strong boundary currents, which we will look at a little bit later on. Was supposed to be a fantastic human being. Built a nice little toy train set in his backyard, which he would make his guests ride. I met him for a brief minutes in Lamont Doherty Earth Observatory at the end of '93. A few months later, he died. He was at a meeting organized by Wally Broker, another giant in the field who just died last year, I think, or maybe early this year. So let's go look at the details of how the circulation actually gets set up. Unlike the surface where the wind stress curl and swirl of transport and closing by the western boundary currents, you need a good explanation for why there is western boundary intensification in the deep ocean as well. Still comes down to beta effects, but we have to explain it, and we'll do that using Taylor columns again. I hope the buzzing didn't destroy this podcast, but I will have to record it again if that's the case. Let's see. I will see.